So how'd you do on this? Get it out, write down what you need, and I'll give you the points. All right. Explain whether or not a normal distribution can be used to model each situation. Explain your answer in a sentence. The migration distances of birds are known to be normally distributed. That's good. With a mean of 3,600 miles and a standard deviation of 350 miles, we wish to know the probability that a random sample of 20 tagged birds will show an average migration distance over 4,000 miles each year. So we just want to explain if this could be done. And the big problem on number one, I love...
What else?
Oh, that's crisp. I'll take that. Good to see you. Good to see you. I didn't have boots on today, I'm sorry. All right, so what do you think on page 77? They've obviously been clocking migratory birds. They have an average, they have a standard deviation. You think this would be good for a normal distribution if we had checked 20 birds at random? I think so. I think we could do it. I mean, now here's the problem with only 20 birds. Okay, what's the number that I said is kind of the minimum we want to go with? 30. 30 is kind of the pivotal point. So what happens is the less amount of birds that you choose has a lot more variability, problems that can take place. So I think 20 birds would be okay if we were using a T sample, but we're not. So I think grabbing only 20 birds, though we'd be able to find a standard error. Square root of 20 is a larger number than square root of 30. So I think you'd want to tag. I think you'd want to take a bigger random sample in that one. Okay, I think your random sample would want to be about 30. Hello. We're on 77. All right. Number 2 says the presence of antibodies in the blood for a certain disease is skewed to the right. Is there anything in that very first sentence that is a red flag for you? Anything that's a red flag in the first sentence? Presence of antibodies in blood of a certain disease is skewed to the right. Any red flags?
Skew right.
Skew right. Thank you. We randomly sample 60 people to measure the presence of antibodies. Is 60 enough? Well, 60 is bigger than 30. Hey. All right. So we wish to know if the sample above is above or below the average, and by how much. So friends, because it says it's skewed to the right, yes, you are totally allowed to have your data be skewed right or left. But do not think that if it's skewed to the right or to the left, it becomes a normal distribution all of a sudden.
My bad.
Okay, talking over too many people.
Sorry.
Okay, it's over there too. All right, shh. We wish to know whether a random sample of 20 cars on I-70 at rush hour will show an average speed of greater than 50 miles per hour. Characteristics of the population of speeds of cars on I-70 during rush hour are unknown. Okay, so we have an unknown parameter, and that's fine. Okay. It says we do a random sample. That's a good idea. But we only did 20 cars. What's the problem? Yeah, it's not high enough. It needs to be at least 30, okay? And so those are a few things to say. It says for the rest of the assignment, note the sampling issues that might diminish our confidence solutions if they exist. Anxiety. Hopefully this class hasn't created anxiety. Good to see you. Good to see you. Oh, that was a good one.
That's what I meant.
All right. So anxiety can often be measured by trained trained psychologist, and is scaled between 1 and 100. Anxiety as a population parameter is skewed to the right. Anything happen there that we need to worry about? Gents. Ladies. Anything we need to worry about so far?
Which one?
Down below, right above number 4. Anxiety can be measured by trained psychologists, can be scaled between 1 and 100. Anxiety as a population parameter is skewed to the right. So skewed to the right, we got to keep that noted. It's skewed to the right. It's not a normal distribution. Okay. Again, it's okay if your data, you find your data comes out skewed to the right. That happens. Okay. The mean anxiety level. Hey, how'd it go last night? Oh. So anxiety, blah, 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 is skewed to the right. The mean anxiety level is 30. Hey, is 30 good enough? Oh, that just says mean anxiety is 30. It's not a population, it's the size. And a standard deviation 20. It says you want to calculate the mean and the standard error. So just because we're skewed to the right doesn't mean we can't do it. So for problem number 4, we tell us that you have a 30 and a standard deviation of 20. Those are both fine. And then calculate the mean and standard deviation. Well, the mean is going to stay the same for our sample. And then if we want to do this changes to standard error, which will be the standard deviation over root 100. So that's going to be 20 over square root 100, which is 10. So our standard error becomes 2. So we can still do that. And in fact, if we do that and we graph that with the standard error, that means our skew to the right becomes a normal distribution, especially with 100 as your sample. Okay? Yeah.
Let's say 10 under the 20 there, 20 over 10.
10, yeah, square root of 100 is 10. Okay, so we have to be very cautious. They already told us to skew to the right. Agree? So that means that the normal distribution would look like this, skewed to the right. If I use this in place of it, it looks like a normal distribution. That's bad. That's bad if we start saying, oh, cool, now we made it a normal distribution. No, you didn't. This is bad news, okay? But we'll still do the math. And then what's the probability of sample size? 100 will show a mean with, between 28 and 32. So there we're going to go Desmos, not YouTube. But YouTube, we could find some fun videos, I bet you. All right, so if I plug in here normal distribution, NARMAL, hey, good to see you. We're on page 77. Normal distribution, and they told us 30. But we're going to plug our standard error in. What do we find the standard error to be? 2. Standard error is 2. Oops. All right. So they want us to figure this out between 28 and 32. All right. So theoretically, and we can't hold our, hang our hats on this, but they say that if we did this and we're just doing the math, that we have about a 68.3% chance that this would have happened. But we have to go back in our minds and remember that it was skewed to the right already. Even though my normal distribution, it looks like a normal distribution when I use the standard error because our sample size is large enough, it is still skewed to the right. So those are things that you have to note. Okay, if it's skewed to the right, theoretically that tail should be on the right side, should be pulled out further than the left side. Okay? Calculate the mean and standard deviation of sample size 25. Okay, so if I want to do sample size of 25, my standard error is going to be 20 over root 25. So that's 20 over 5, or 20 over 5, which is 4. So there's my standard error there. Okay? So, and then the mean stays the same. The mean stays consistent on these. All right. Find the probability of a sample size 25 will show mean anxiety level between 28 and 32. Okay, if the sample size is 25, that's a red flag because it's not what number? 30. Okay, but we're still going to play with it. So we're going to change this up here to 4, I believe. Isn't that what I came up with? And between 28 and 32. So if we do this, that becomes a 38.3% chance. That's where you get the wiggle room. You have things that are happening on the left, happen on the right a lot more often. Okay, that happens with a low sample size. That's why we want it. They claim 30 is the nice number as far as we know right now. All right. For 8-9, it says the length of films released by Hollywood are known to be normally distributed with a mean of 115 minutes and a standard deviation of 15 minutes. Okay, so anything in there that's bad, they say it's normally distributed. Good? Should we stick with it? Do we trust it?
No.
It says it's normally distributed.
Yes.
That is a yay. Okay, it's not skewed right or left. Agree? All right. So we want to find the probability a single randomly chosen film is less than 95 minutes long. So what I'm going to do is I'm going to come up here. I need to change this to the 115 minutes. Oops. And change this to 15. So let's do this. And then we want to see find the probability a single film is less than 95 minutes. So this is going to be our negative infinity. So, and then we want to change this to 95. Okay. So the probability in this situation, if you found a film that is less than 95 minutes long, it has about a 9.1% chance that you found that. Find the probability that a random sample of 9 films, okay, 9 films, you increase your variability. Agree? 9's not 30. 9's less than 30. But we can still do it. So let's figure out what our standard error would be in this case. I'm going to come back here. And I'm going to go 15 divided by, and I know we could have done this in our head, divided by square root of 9. So yes, you could make that 3 and you can make it 5. And then a film is greater than 120 minutes in length. All right, so in this case, because we're only choosing 9 films, it seems that we have like if we were to select 9 films at random, what's the probability they're 120 minutes or longer? In this case, it comes to about a 16% probability. 16% probability could happen. But that square root 9, this 9 right here, that 9 right there, that's kind of iffy. All this is basically telling us if we randomly selected 9 films from the whole category of all the films, we have close to a 16% chance that it would be 120 minutes or longer. Okay, I don't like our sample size that we're selecting, but it's still there. We still work it. And then the average electric bill in Denver is skewed right. Does anything stick out that's bad there? Anything that we have to note there? Skew right. We don't want that. Has a mean of $145 and a standard deviation of 50. Okay? So the hard thing about this is we know it's skew right, but then they want us to create a normal distribution with all 7 physicians. Okay? We know it's skew right, so this is going to be off. So I'm going to add 50. That gets to 195. Add 50, 245. Add 50, 295. I think I did my math right. Subtract 50, that's 95. Subtract 50, that's 45. Subtract 50, that is negative 5. Okay? Oh, geez. All right. And then we want to do, so that's basically on our distribution. But if we wanted to change this with a sample size of 16, you're going to get your standard error, which is going to be the square root's in the wrong spot. It's going to be the 50 divided by the square root of 16. Hello. Good to see you. So we're on page 78. So that's 50 over 4, which is like 12.5. So basically, I would add 12.5 to get here. I would add 12.5 to get here. I would add 12.5 to get here. I would subtract 12.5 to get here. I would subtract 12.5 to get here. Subtract 12.5 to get here. Okay? Describe the electric bills that are exactly one standard error above the mean and one standard below the mean. So 145 plus 12.5 is 157.5. So 157.5 is the top end. And if I were to subtract 12.5 from 145, I don't know, I can't do it in my head. So come on, Stirp, you can do this. No, I can't. That's a 143.5. Nope, 133.5, sorry. So 133.5 is our lower. Okay, so basically, if we were doing really bad statistics and we were relying on the standard error in place of the standard deviation, and if we rely on the standard error, that means that our normal curve looks like a normal curve, even though our original is a skew right. That would mean that roughly 68% of my data would fall between 133.5 and 157.5. So we have basically a 68% chance that if we continue to take a sample size of 16, that they would fall within that parameter or that region. And then use the 68. Okay, so this would be your 68 region, this would be your 95 region, and this would be your 99.7 region. And again, my friends, we are using the standard error to make our skewed distribution look like a normal distribution, which is a huge red flag, and we should smack you around if you do that. Okay, friends, we have a quiz tomorrow. It is a front and a back. Okay, so I think we are pretty good. Let me teach this next stuff. And we should be good. I think we can handle it. Yeah, I'm off a day up there. We're only doing up to 5.5. All right, which is fine. The quiz only goes through 5.5. All right, so ready? Proportions, percents, and decimal form can also form. This is on page 11. Can also form normal sampling distributions for large samples. Before we get to the calculations, you find the variables. Okay. So they're going to say that P is the population proportion. So this is either a fraction or a decimal. And I'll show you how to get to that in a little bit. And then you have P hat. This is like the predicted. Yay, I knew it was going to happen. So the P hat is the sample proportion. That's what we're predicting. Okay? And then you have mu, it looks like a little U with a big old tail at the end. With P hat, that's the average proportion from all, possible random samples. And then we have a little O with a tail at the top with a P hat as a subscript. And that is, I don't remember the Greek letter. Standard deviation of the proportion of all possible random samples called standard error. Okay, that's going to be our standard error. Okay, so if we knew in this case that we knew that 25% of the population had type O blood. Okay, like we we worked at a blood bank, and all the blood is recorded into a central database. If they go and take a look at the database, they see that 25% or 0.25 is of people have type O blood. And then they tell us that P hat is 28 out of 100 in this case. So they tell us that assume 25% of the people have type O blood. We conduct a random sample of 100 people. So now we go with 100 people, and 28% of those 100 people have type O blood. Okay, so this is 0.28. That's P hat. So if we randomly sampled 100 people, is that enough people to randomly sample? Yeah, it's above 30, so it's good. Okay. So we've done that math. Of course, we expect the proportion of people with type O blood to vary somewhat from sample to sample. These varied random samples for sampling distribution with mu p hat and standard deviation formulas are provided. Okay, so they're going to provide us with these. They say mu at p hat is equal to p, and again, p is the prop. This was the entire percent as a decimal or fraction. Okay, and then they tell us that mu at p hat. So our new standard error equation is going to be this. It's going to be p minus 1 minus p over n. Do what I do?
Good, I'm just like going over this.
Oh, okay.
Make sure like we know our process.
Yeah. All right. This is now how we're going to find our new standard error. This is how you find standard error when you're given it as percents. Okay? Percents don't give you an actual number, but we know that the probability is 25 or 0.25 minus, and then 1 minus 0.25 divided by our sample size of 100. And if you did this on a calculator, they have it already written for us, but if you plug that into a calculator, you're going to come out with 0.0433. Okay? This is my new standard error. Okay? Which basically means we know that this is 0.25. So if you were to add or subtract 0.043 from 0.25, that's what you're using to create your normal curve. Okay? Random assignment on top page 12, almost done. Random assignment. The individual selections in the sample were randomly chosen from the population of interest. Okay, we've talked about randomness. It implies each individual in the population of interest had an equal chance to participate. Independence. We've seen this term before. What are they saying about independence? The probability in an individual's response was unaffected by the conditions in which other selections were made. Okay? So you're not changing it. It's like, oh, look, we pulled this person who has blonde hair, blue eyes, so let's eliminate all the blonde hair, blue-eyed people from the next sample. No, you're not affecting it at all. Sample size is large enough. Sample size suffer from high variability. You don't want to draw conclusions about the population based on a small sample. Okay, for means, the random sample had to be 30 or larger to give us confidence that the sample distribution will be normal. For proportions, the rule of thumb is a bit different. So what we do here is we go, is n times p greater than or equal to 10? And then is n times 1 minus p greater than or equal to 10? So these are two tests. These are two tests to verify if it goes into place. Meaning, because we're using a percent, because we're using percents, like if I had 3% up there, I don't know how many people I used to get to 3%. Does that make sense? They're just telling you, hey, 3% this happens, or 25% this happens, or 80% this happens. Okay, we don't know how many people we're using, so what we have to do is we use these two equations to verify if it works. Okay, so P is the proportion that's given, whether it's a fraction or a decimal. And then N is the sample size. Okay, so if we had something that was just randomly given, let's say they told us that 30% of something with a sample size, so this is your P, and let's say we had a sample size of, let's say we had a sample size of 60. What we have to do is then we have to go 60 times 0.3. Is that greater than or equal to 10? Well, that comes out to 18, excuse me. That comes out to 18. Is 18 greater than 10? In this case, it is. And then if I do the same thing here, I'm going to go 60, and then 1 minus 0.3. Is that greater than or equal to 10? And again, this sample's not in there, so that's 0.7. Is that greater than 10 here? So that means is 42 greater than 10 or equal to 10? It checks in both these situations for our sample size. That basically means what this is checking is, was my sample size large enough to say that we could conclude that this could work? And basically, it's just a matter of plugging into those two equations. They're relatively easy, but that's what we have. So, come Monday.
I think it is maybe 1/2.
Did I make a mistake?
No.
Oh, okay.
You're right.
Okay. We'll go over this on Monday. Will be page 79 and 80. And then Friday, which is tomorrow, one of them being tomorrow, we will have a quiz. And it's 5-1. to,
5-5?
it's actually more of 5 to 5-4.
Yeah, I'm not gonna lie, 5-5 is kind of.
Okay, so that's why on Monday we'll go over what this was, and we'll be happy.